path of x won't let me record. Okay. All right. So, a polynomial is an expression of more than two algebraic terms. Okay, some of this stuff is stuff that you talk about in Math 1 also. Terms are pieces of an algebraic expression. So when I say algebraic expression, we're thinking like 5x squared minus 3x plus 2. That's an algebraic expression. The terms of that expression are separated by plus and or minus signs. So just to give you a real quick example, if I have something like x to the third minus 4x squared plus 7, okay, that would have 1, 2, 3 terms, right? 3 pieces of that expression that are separated by your plus or minus signs. That'd be 3 terms. Okay, that's going to be important here in a minute when we work on naming these. I want to work on talking about that. Well, I'll do that when I get there. All right, another thing we need for naming polynomials is we need to know the degree of a polynomial. So, the degree of a polynomial is the greatest exponent of a variable in an algebraic expression. So the greatest exponent of a variable in an algebraic expression. To give you an example for that, if I have x to the third minus 5x squared plus 10x minus x to the 7th. Okay? What would the degree of that polynomial be? 7, right? So this would be a degree of 7. It doesn't matter. The only thing you're looking for that is your exponents. Okay? So highest exponent. So you're just looking at those exponents. It doesn't matter that this had a 10 right there. 10's higher than 7. It doesn't matter because that's not an exponent, right? Okay, questions? All right. So, there are special names for certain types of polynomials, all right? They can be named both by degree and by your number of terms that you have. So, when we're talking about degree, if your highest exponent is a 0, this is kind of weird because if you have x is 0, it really just equals 1. That would really mean that x is missing. Then that would be called constant. You won't see that happen a lot. If the highest exponent is 1, then it's linear. 2 is quadratic. Think 2 is x squared, right? Those were quadratics that we looked at. 3 is cubic. 4 is quartic. And if you have 5 or more, there is no special name. So you would just say a polynomial of 5th degree. Just have 5th degree there. So, or if it was 6th or 7th or 8th or 9th. If it goes beyond 5, there's no special name. You also name these by the number of terms. So if there is only one term, technically here, if there is only one term, technically this is not actually a polynomial. But I'm putting it in this section because we're just naming some terms here. Because what does that prefix poly mean? More than one, right? So if you only have one term, it's actually not a polynomial. It's called a monomial. A mono meaning one. 2 terms is a binomial, like a bicycle has 2 wheels. Trinomial is 3, like a tricycle has 3 wheels, right? And then when you go past that, there are also not special names for those. So we would just say that it has 4 terms or 5 terms or 6 terms after that. Okay? Naming these can be important because sometimes you will have problems that use these words. And they're big, complicated words that throw kids off whenever really they're just telling you something about the degree and the number of terms. So that's why I want us to spend just a little time talking about these terms here. So let's just do a couple examples together, and let's try the rest. So if I look at the first one there, I need to know two things. I need to know the degree, and I need to know the number of terms. So when I look at the first one, Katie, what is the degree for the first one? It is 3, right? I'm looking at that exponent right there. Degree 3 was cubic. If you look back at that last slide, right? A degree of 3 was cubic. And then I'm looking for the number of terms. I've got 1, 2, 3 terms. What's the special name for that? Trinomial. You guys see what's happening there? Try the rest of those. Name the rest of those for me. If it's 5 or over, you would just say 5th degree. Yeah. Or 6th degree. And in general, we usually say the degree first, and then the number of terms second. Okay, so let's look at these. Carlos, what would I call the second one? Not square. Binomial is correct, though. If we have a second, that is x squared, but it's called a quadratic. So it is a quadratic binomial for that one. Okay, 3 is probably your most complicated. Who wants to try that one? What you got, Passion? All right, polynomial of 5th degree with 4 terms. Perfect. Or you might see a 5th degree polynomial with 4 terms, or you could word that a couple different ways, but 5th degree, 4 terms. Very good. All right. Let's see. Elijah, what about number 4?
It is the quartic, and it's
Quartic monomial. And let's see, Aiden, what about the last one there? It is not constant. Binomial is correct, though. It is a, you're correct, that x does have an exponent of 1, but look at the word for degree, not for the number of terms. So degree, if we have a degree of 1, it is linear. Linear binomial. Okay, so I'm not going to give you a lot of questions about that, but sometimes they throw it in the middle of a problem, and it can be confusing. This is all it's talking about is the number of terms and the degree of the function. And degree is important for us to understand because we have to talk about the fundamental theorem of algebra, which deals mostly with degree. All right, so here are a couple terms that we have to know for this section as well. You will see this used pretty often in this unit, the term zeros. Okay? And whenever we're talking about zeros, this will be called the x x-intercepts of a function. So it's the places where your graph crosses the x-axis. It is also sometimes called, these are also sometimes called roots. Another term you're going to see is solutions, and the solutions are the values that make an equation equal 0. Now, the difference in these, that all of these terms more or less mean the same thing. Zeros, x-intercepts, I'm not sure about roots. I've seen it in both places. I'd have to go look at that more closely. But definitely zeros and x-intercepts, these are usually going to be of a function. And solutions are usually of an equation. So let me just show you the difference between those, because they might be like, that sounds like the same thing to me. A function would be like if you have f of x equals 3x squared minus 4. Or it might not have f of x, it might have y equals something like 2 minus 3x to the third or something like that. Plus 7x, it doesn't matter. Right? So it either has an f of x or y equals. You can graph it in Desmos. Right? An equation does not have a y or a f of x. It might be something like this. 3x squared minus 4 equals 0. Or 5x minus 3 equals 2x plus 7x squared. Those would be equations. There's no y or no f of x in there. You've just got two things set equal to each other. We're going to talk later about how those are related. And I think it's incorrect. Occasionally you'll see solutions of a function, but I don't think it's actually right. But these terms, more or less, zeros, x-intercepts, roots, and solutions, are all looking for sort of that same thing, that value that makes the equation equal to 0. Okay, it might be an equation or a function, but what makes that equal to 0? So we're going to see these a lot. All right, so fundamental theorem of algebra. This is an important day in your career as a mathematician to learn the fundamental theorem of algebra, because obviously somebody thought it was pretty important to name it the fundamental theorem of algebra. The fundamental theorem of algebra states that every polynomial function of positive degree n has exactly n complex zeros. So let's not use yellow there. Zeros. And again, this is sort of restating this, but zeros are values that cause the function to have an output of 0. That's why they're calling them zeros. If you plug a number in and get 0 out, that is why they call those zeros. Now, you should see a word that you probably don't like right there. Complex, right? That does not sound good when dealing with mathematics. We'd rather see simple than complex, right? So, we're going to talk about in a little bit what is the difference between a real 0 and an imaginary 0. Now, I've really said something that you hate to hear, right? Why are we even studying something that is imaginary? But we'll get that whenever we get there. Complex means that they might show up as x-intercepts, but they also might just make the function 0 without that. So we do have to do a little bit of that. Okay, so the application of this is pretty straight. Well, so we got to do this here. So basically, let me just give you a quick example before we go into this. So basically, if I have a function like this, if I've got f of x equals x to the fourth minus 3x squared plus 2, what is the degree of that function? It is 4. That tells us that f of x has exactly 4 zeros. That's basically all the fundamental theorem of algebra says. It says if you got 4th power, you should have 4 zeros. If you had 7th power, you should have 7 zeros, right? That is basically all that we see. However, whenever, I just made that up off the top of my head. I said zeros can be x-intercepts, right? Let's see about what I've just came up with here. Let's see if it has 4 x-intercepts. If I graph this real quick, if I graph f of x equals x to the fourth minus 3x to the second plus 2. That one's got 4. It crosses 4 times. Let me change that to a 7 right there. Oh, does that one have any x-intercepts? No. But fundamental theorem of algebra tells me that both of those have 4 zeros, right? So obviously there has to be something a little bit different in those two situations, because if that has 4 zeros, not all the zeros are necessarily x-intercepts, right? Now, if I go back to what I had before, if I had the plus 2, my 4 x-intercepts, those 4 places where I cross the x-axis, those are my 4 zeros of this function. So this function has 4 zeros, and I could find what those are. But that's not going to be the case for all of these. So let's talk about the different kinds of zeros that you can have. All right. So the first type is the type that we just saw whenever I graphed that first function, real zeros. Real zeros are the x-intercepts of a function. Okay. So real zeros are going to be something that we can see on the graph. All right. Then we have this here that you guys are going to love. Imaginary zeros. Okay. What I find difficult about how to teach this is that you guys have not seen this value right here, I, yet, as far as I can tell. The only person that told me they have seen it and know it, I think Miss Martin did say she did do a little bit of this in Math 2, just a little. So you might, if you've had Miss Martin, you might have seen it, just don't really remember what it's about. But I is what we call an imaginary number. Now, some of you are instantly like, this is even stupider than adding letters to math, all right? Because now you're telling me that we care about something that's imaginary. It doesn't even exist. Why did we do this? What I is I is a way of dealing with the square root of a negative number. Because if you try to take the square root of a negative number, you can't do it. Square root of a negative number means what number times itself would give me this value, right? So is there any number times itself that would give us negative 1? There could not be, because like if I did negative 1 times negative 1, it'd give me positive 1, right? You can't take a square root of a negative number because any number times itself is going to give you a positive number, right? So, but what happens is that whenever we're working with algebra, a lot of times we end up with a negative underneath the square root. We're trying to solve a problem and we end up with a negative under the square root. So mathematicians said, in order for us to deal with this, let's call this I. Okay? And then they named it the imaginary number, right? So it's really just the square root of negative 1 whenever we're talking about that. And it helps us deal with it. They tell me that I's are used in all kinds of really important things, like something to do with the networking of cell phone towers has a lot of imaginary numbers in it. Obviously, I'm not a network engineer for a cell phone tower company. I don't exactly know how that works, but you got to get to a pretty high level before you're actually using those imaginary numbers. The good news is we only have to know it on a very basic level, right? We just kind of have to understand that these are here. We don't necessarily have to be able to find them and use them a lot. This last part here, imaginary zeros, they still cause the function to equal 0, but they do not show up on the graph. These values include the imaginary value I. So if you have an imaginary 0, it will have an I in it somewhere, and they won't show up on the graph. Imaginary zeros always come in pairs. This is important. So, if x equals 3i is a 0, then x equals negative 3i is also a 0. That's going to be important on some of the questions that we see in the future. Because if you have one imaginary 0, you got to have another one to go with it. They always come in pairs. Right? Okay. Another thing we're going to talk about with zeros is some zeros. In fact, let's see if I can go over to that. I think I already shut down that. No, maybe I didn't. Okay, let's see if I can go over to this graph right here. Let me just get rid of that +2. No. Let's see. Let's do plus 2.25. Okay, yeah. All right, so if I take this graph that I was just looking at, this has a degree of 4, right? X to the 4th minus 3x squared plus 2x to the 25th. But if I look at the graph, how many x-intercepts do I see? Now I only see 2, right? So this graph still has 4 zeros. And all 4 of them are actually real zeros. But what has happened is some of them are repeated zeros. So right here, at this point, at negative 1.225, I've got 2 zeros at the same point. And over here, I also have 2 zeros at the same point. All right. So let's talk about how we can tell that that has happened from the graph. Okay. Real zeros with an odd multiplicity will cross the x-axis. So they will go all the way across. So if I have a graph that looks like this, I know these 3 points right here would be real zeros, and I would know they have odd multiplicity. Probably they're just like a single multiplicity. There's only one of them there. But it is possible that there's 3 or that there's 5 at that point. I would need to know the degree of my function to be able to tell. If I have real zeros with an even multiplicity, we'll touch the x-axis but not cross it. That's what we were just seeing in that graph. Right? At these points, it's like the graph just goes down to the x-axis and it's like it just bounces off of it. Right? It touches it and goes the other direction. So for those 2 right there, I would know they have even multiplicity. At least 2. But it could be 4 or 6 or 8 or anything even right there. I need to know the degree of my function. Okay. So odd multiplicity, you're going to cross. Even, you're going to bounce off the graph. All right, let's keep going. Here. All right, so, okay. I need to identify each real zero and tell if it has even or odd multiplicity for this. Okay, so we're only talking about real zeros right now, so we're just looking at this graph. Real zeros are going to show up on the graph as what? What is it? Where do I have real zeros on the graph? Which line? X-axis, right? So x-intercepts. right? So for this one, we hit the x-axis here, here, and here, right? So my real zeros for this one would be at x equals -2, x equals 0, and x equals 1. I know that looks like a 2 right there, but notice that the scale's off a little bit there. So, for this, I need to tell if it has odd or even multiplicity. At -2, is it going to be odd or even? It's even, right? So, even multiplicity. Whenever it like goes down and bounces off the x-axis, so you don't actually cross the x-axis, you just go down and touch it and then come right back up.
Okay.
So at -2 right here, that's what happens on my graph. I'm tracing it here. I go down, I touch the x-axis, but then I bounce back up. What about at 0 and at 1? Is that odd or even multiplicity? Those are going to be odd. So both of these would be odd multiplicity. There. And that I know is odd because I crossed the x-axis. I'm above, I'm now below, or I'm below and now above. So those would be odd. Okay, try the second one right there. Try that one on your own. You should be listing out your zeros here, like I did. Let's check and see what we've got here. Here's what you should have. You should get real zeros at -1, right here, 0, 1, and 3. So those are your 4 distinct zeros. The first two, -1 and 0, are odd. The next two, 1 and 3, should be even. Here's a question for you. What is the lowest degree this polynomial could be? It tells me, all right, so the number of zeros I have has to match the degree of the function, right? I have 4 zeros, but what do I know about these even zeros right here? They have at very least got to be double zeros, right? So, like, it could be that there's 4 zeros right here at x equals 1, but, like, it would be listed twice, and this one would be listed twice, right? Odd, the very lowest you can have for odd zeros is just you have 1 single zero there. If it's even, the very lowest you could have would be 2, right? So the very lowest degree I could have for this would be 6, because -1 and 0 could both be just single zeros, and at 1 and 3, those have to be, at the very least, they've got to be double zeros. So you would have x to the 6th power would be your degree lowest degree you could have. It could be higher because you could have, like you could have 4 right here. We'll look more at that. A second, just throwing that in there. Okay. All right, so here's an example where you got to consider that. Okay. All right. The function to the left is they're telling us the degree. It is a 5th degree polynomial. Okay? So if it is 5th degree, how many zeros does it have? It has 5 zeros. Okay? So that means that over here, my real zeros and my imaginary zeros need to add up to 5 because I've got 5 zeros, right? So how many zeros do I have on this graph? I've got 2. Don't write this down because this is wrong. So if I got 2 here, that means I'd have to have 3 imaginary. But I told you imaginary have to come in pairs, right? Can you have 3 imaginary zeros? You cannot. Okay? Imaginary zeros, this needs to always be an even number. Because imaginary zeros have to come in pairs. So let's back up. Let's not put 2 and 3 there. Now I do only have 2 zeros on my graph. But let's think about multiplicity. X equals 0 has an odd multiplicity, right? What about x equals 2? That's even because it's just bouncing off the graph right there. So, x equals 2, I like to call it a double 0. It counts twice. So if we're like listing them out, we would have x equals 0, x equals 2, and x equals 2. Okay? Because if you just go down and barely touch the graph and come back up, that is a 0 with multiplicity of at least 2. Now, it could be 4, but can it really be 4? I guess technically it could. I should add some more information. Technically, I guess maybe it could be 4. It could be 4 and this is 1 and that adds up to 5. That's technically a possibility. I should add some more information to this. But let's just go with this. So you actually do have 2 options, I guess. We could have that x equals 2 is there 4 times, and then x equals 0 is your other. So that's a possibility. We could have 5 real zeros and no imaginary zeros. That's a possibility. Or we could have 3 real zeros and 2 imaginary zeros. So you could either have x twice or x 4 times. And that would give you the difference for these 2. I should reword that question so it doesn't have 2 answers to it. Okay, but notice this always has to add up to 5. These numbers must be even. Imaginary numbers always come in pairs. All right, let's look at another question. Okay. All right, this one only has one answer, is a 6th degree polynomial. So if it is 6th degree, how many zeros does it have? It's got 6. All right, how many do we see on the graph? I got 1, 2, 3, 4, 5. Okay. Now, is this possible I got 5 real zeros and 1 imaginary? That cannot happen because imaginary has to be even. So, if I look at my graph, which one of those could be a double 0 right there? That first one right there where x equals 0. It just bounces off the x-axis right here. Right, so this one right here is a double. And in this case, we know it's got to be double. It can't be 4 times because we got 4 other zeros, and we can't have more than 6, right? So we would have just 6 real zeros here and 0 imaginary. Okay, questions? All right, let's go to the next one. All right, here's where we're gonna start to need our Desmos. So if you want to pull up Desmos there on your computer, we'll use it here. Let's type this big long equation in. Oh boy, I don't see much here. If I just zoom out to try to see that graph, that doesn't look good, does it? It looks like I just have zeros right here. I'm going to go here. I really need to see more of the top and bottom of the graph, but as far as how wide it is, it's okay. So I'm going to go here and make my y-axis maybe negative 100 to 100. Let's see what that does. That's better. I still can't see the bottom, but I'm pretty sure that just goes down and comes back up. So they're telling me that this function has zeros at x equals 5. Well, I can see that on the graph, right? There's that 0. And at x equals plus or minus I. I'm supposed to tell the number of real and imaginary zeros. Okay, so what degree is this? It is going to be 5 because right here, that's my highest exponent. That means real and imaginary together has to equal 5, right? X equals 5, that is real. What about x equals plus or minus 3i? If it's got that I in it, it's imaginary. Now, imaginaries always have to come in pairs. This is a pair. It's a positive 3i and a negative 3i. Putting that plus or minus in front of it means there's really 2 right there. So, I have at least two imaginary zeros, right? I know these are imaginary. There's 2 of them. I have this other real 0 right here. So looking at this graph, are my other 2 that are missing, because I got to have 5, right? I know I've got, we're going to keep tally. I know I've got 2 imaginary over here. I know I've got 1 real 0. I got 2 more that are missing. So looking at this graph, are those other 2 going to be real or imaginary? Real? Where are they at? On this graph, I know it's kind of small there. They're right here at negative 1, right? And they're the same 1 because we have a double unit there. So we got 3 over here. We got 2 imaginary zeros. Let me show you what it would look like if it were going to be 4 imaginary zeros. If it were 4 imaginary zeros, let's change this to 48. It would look like this. Okay. How many real zeros would that one have? Just 1, right? So that would mean the other 4 need to be imaginary. Or I guess maybe you could have a double right there, but that's not what we've got anyway. We've just got 1 answer for this. Okay. All right. Oh, didn't go back. All right. So let's type in this next one that we've got here. We got x to the 4th minus 8x to the 3rd plus 14x to the 2nd plus 28x minus 80. Oh, that's a weird looking graph. Alright, so this function, first of all, what degree is it? 4. How many zeros has it got? 4. Okay. It has, I've worded that poorly. It has, that's a typo right there. It should say it has a 0 It shouldn't say zeros, A0 there. That zeros should not be there. It has A0 at x equals 2 plus I. Tell the number of real and imaginary zeros. So tell me about this 2 plus I. Is that real or imaginary? Imaginary. Now, this one is just one imaginary number, but is it possible for me to have a 1 right there? It is not. So if I have one imaginary number, it has a buddy that goes with it, right? So even though they didn't tell us both of the imaginary numbers like they did in the last problem, I know I've got to have at least 2 right here. So I've got at least 2. My question is, are those other 2 that are missing, are they real or are they also imaginary? So I'm going to go to my graph. Do I have real zeros on this graph? Real zeros are going to be x-intercepts, right? Do I have x-intercepts? I've got 2 of them right here. I got one right here at -2. I got another one over here at 4. So I have 2 real zeros. All right, so I have 2 imaginary, 2 real on this. Okay, questions? All right, let's keep going. All right, end behavior for these. So end behavior, I think this is a little bit easier than the end behavior for, the exponentials and logs that we did. But the idea is still the same. You're going to have, as x approaches negative infinity, y approaches blank, or it might say f of x approaches blank. As x approaches infinity, y approaches blank. So all we're doing here is we are looking, this right here, as x approaches negative infinity, we're looking at the left side of the graph. And as x approaches positive infinity, we're looking at the right side of the graph. Okay? For these problems, they should always be infinity or negative infinity. These problems do not have horizontal asymptotes, so they are not going to even out at a number. So if I look at this graph on the left-hand side, what's happening on the end? Am I going up? Am I going down? Am I evening out at a number? On the left-hand side, we're going up, right? What about the other side, the right side? Or am I going up, down, or evening out at a number? Up, right? So ups are positive infinities, downs are negative infinities. I should get an up, positive infinity, and another up right here. Now, certainly on a lot of these you could just graph them, but there's a shortcut you can use for this. So if you have an even degree, so if you have something that's 2nd degree, 4th degree, 6th degree, 8th degree, the ends of your graph should go the same direction. So I know this one is an even degree problem. It's either 2nd, 4th, 6th, or 8th, or 10th, or something like that. So even degree, if you have a positive number in front of your, it's called a leading coefficient. It's the number in front of your highest exponent. So like, for example, if I had y equals positive 4x to the 6th, right? Even if I have like a minus 2x squared over here, you're only looking at the number in front of your biggest exponent. If I have a positive number in front of my highest exponent, and it's an even one, both will go up. If I have a negative leading coefficient, both will go down on both ends. Odd degree, if I have odd degree, then we will have this situation where our two sides are opposites, right? If we have a positive leading coefficient, negative will be negative, positive will be positive, right? On the left side is negative, on the right side is positive. If we have a negative, it flips that, and we have the opposite. It's true. So if we look at these problems over here, right? If I'm doing end behavior for number 7, right? As x, that arrow means approaches. As x approaches negative infinity, that just tells me I'm looking at the left side. Okay? On the left side of that graph, Ayla, what do I have? Am I going up? Am I going down? Am I evening out a number? Up, so that's going to be positive infinity. Okay? over here. Wade, as x approaches positive infinity, which means I'm looking at the right side of this graph, okay, is that graph going up, down, or evening out at a number? Down, and so for down, we will use negative infinity. Okay? For 8 and 9, it asks us to describe the end behavior. You can go type this in, and then you're just looking on the ends. Do I go up or down? Or, if we have odd, that means it's either going to look like this, or it's going to look like this. This would be for our positive. We have a positive number in front of our highest exponent there, so we're looking at something that's going to look kind of like this. Right, so on the left-hand side, as you approach negative infinity, you go to negative infinity. On the right-hand side, as you approach positive infinity, you go to positive infinity. Or you can type it into Desmos and look at it. What is the degree on number 9? 4. When we have even degree, that means they're both up or they're both down, right? And so we're going to look at that term that we get our degree from, and if that is negative, they'll both be down. If that is positive, they'll both be up. And so since we have a negative right there, it's going to be negative infinity and negative infinity. And you can always, if you're not good at keeping up with those rules, I am probably going to let you use a note card on this one as well, so that little chart could be something good to put on your note card. If you're not good at keeping up with the rules, you can always graph these and look at what's happening. Okay? All right, questions? All right, moving on. All right. Okay. Here I have 4 different equations. And we are supposed to look at the roots of each graph and describe how the values of the real zeros relate to the equations. So I want us to look at that first one. I have a 0 right here. I got x equals negative 1. Does it have even or odd multiplicity? It's going to be even. Okay. Then I have another one right here. Looks like it's about x equals 1/2. Does that have even or odd multiplicity? That is odd. And right here, I have x equals 2. Is that even or odd? Even. All right, look at the equation. Okay, this equation is in what we call factored form. If it's not in factored form, it doesn't help you a whole lot. But if I look at the equation, I got an x plus 1, an x minus 2, and 2x minus 1. Well, I had an x plus 1, and I had x equals negative 1, right? I also had x minus 2, and I had an x equals 2. And then I had this, and I had an x equals 1/2. Okay? What these are they're the values that make this piece 0, right? Because we're finding zeros. That should make sense, right? So if I put a negative 1 right here, it makes this 0. If I put a 2 here, it makes this part 0. If I put a 1/2 right here, 2 times 1/2 minus 1, makes that 0. All right? Notice, what do I have for my exponents? I've got an even exponent right here, an even exponent right here. I don't have an exponent here, but if I had one, it would be a 1, which is an odd exponent. So we should see that kind of happen. Let's look at one more right here. I'm not going to do all 4 of these because we're running out of time. I've got x equals negative 1, and I got x equals 3. Okay? This one would be even. This one would be odd. Right? If I look at my equations, I got x plus 1. Well, x equals negative 1 goes with that, right? And I've got x minus 3. So x equals positive 3 would go with that. And notice this has even multiplicity. My exponent is 2. This has odd multiplicity. My exponent is 3. There. Okay. If I'm just looking at the equations, what causes the graph to bounce off the x-axis? There. So it should be multiplicity of 2 or an even number in this case. All right. Let's see what I've got next. We're going to hold off on this. I want to do it tomorrow because I'm losing a lot of you.